Hello and a very good evening. Here's Stellar Embers Group presenting White Dwarf Stars, the stellar embers of the universe. Here's our team members. What is White Dwarf Stars? White dwarf stars are the dense remnants of medium to low mass stars that have exhausted their nuclear fuel. About the size of Earth but as massive as the Sun, they slowly cool over billions of years, serving as cosmic clocks for measuring the universe's age. While no longer undergoing fusion, white dwarfs play key roles in phenomena like nova and types of supernova, offering insights into stellar evolution and the universe history.
Formation of white dwarf. First, the stars generate energy through nuclear fusion, fusing hydrogen into helium in their cores. Gravity powers this fusion, releasing an enormous amount of energy. The energy from fusion pushes outward, balancing the inward pull of gravity. This balance keeps the star stable during its life. When the hydrogen in the core is exhausted, the core contracts under gravity. The outer layers expand, transforming the star into a red giant. In the red giant phase, helium fusion begins in the core, producing carbon and oxygen. The star expels its outer layers, forming a planetary nebula, a glowing shell of gas and dust. More than half of the star's mass is lost into space. The remaining core, made of carbon and oxygen, becomes a white dwarf. It is kept stable by quantum forces that resist gravity. In conclusion, white dwarfs are the final stage of stars like our Sun. These stellar remnants help us understand the life cycles of stars and the universe.
For the physical characteristics, first, let's talk about their size and density. White dwarfs are tiny compared to normal stars. Imagine taking a star the size of our Sun and compressing it down to the size of Earth. That is a white dwarf. But don't let their small size fool you. They are unbelievably dense. A single teaspoon of white dwarf material would weigh several tons, enough to crush almost anything on Earth. Next, the mass. Despite their size, white dwarfs can have a mass comparable to our Sun. However, there is a limit 1.4 times the Sun's mass, known as the Chandrasekhar limit. If a white dwarf exceeds this limit, it could collapse further into a neutron star or even a black hole. Other than that, the composition of white dwarfs. Most white dwarfs are composed of carbon and oxygen nuclei, left over from the star's core after nuclear fusion ends. A thin layer of hydrogen or helium often surrounds this core, creating a unique chemical signature. Temperature. When white dwarfs form, they are incredibly hot, with surface temperatures exceeding 100,000 Kelvin. Over billions of years, they gradually cool, radiating their heat into space. Eventually, they fade into theoretical black dwarf. Though the universe isn't all enough for us to observe one yet. Luminosity. Although white dwarfs are hot, they are dim because of their small size. As they lose heat, they become even fainter, slowly disappearing into the cosmic darkness. Gravity. One of the most mind-boggling features of white dwarfs is their surface gravity. It's hundreds of thousands of times stronger than Earth's gravity. Light escaping their surface is even redshifted due to this immense gravitational pull. Lastly, the magnetic field. Some white dwarfs exhibit intense magnetic fields, far more powerful than Earth. These magnetic fields can affect the star structure and behavior, creating fascinating variations among white dwarfs.
The Chandrasekhar limit. Understanding the stability of white dwarf. The Chandrasekhar limit is the maximum mass a white dwarf can have before collapsing, approximately 1.4 times the mass of the Sun, named after Subrahmanyan Chandrasekhar, who discovered it in 1930s. What causes the limit? 1. Supported by electron degeneracy pressure. A white dwarf's stability comes from electron degeneracy pressure, a quantum mechanical force that resists compression. Second, when mass exceeds 1.4 solar masses, gravity overpowers degeneracy pressure and collapse occur. This causes the stars to collapse, potentially forming a neutron star or black hole. Significance of the Chandrasekhar limit determines the star's end life. The limit predicts whether a star will remain a white dwarf or collapse into a neutron star or black hole. Highlight electron degeneracy pressure. It shows how quantum mechanics resists gravitational collapse in stellar remnants, interaction between physics and gravity. The limit demonstrates how quantum mechanics and gravity work together to shape the structure and stability of stars. The Chandrasekhar limit is a fundamental concept in astrophysics. It explains the fate of stars and the transition from white dwarf to more extreme projects like neutron stars and black holes. It bridges the gap between quantum mechanics and general relativity in stellar evolution. Here also the equation that related to Chandrasekhar limit.
Significance in astronomy. Among the stars scattered across the cosmos, white dwarfs stand as silent witnesses to the life cycles of stars and the evolution of the universe. But why are these stellar embers so significant to astronomers? Let's explore their importance in unraveling the mysteries of space. White dwarfs represent the final chapter in the life of medium-sized stars like our Sun. By studying them, astronomers gain valuable insights into stellar evolution, revealing what happens as stars exhaust their nuclear fuel. In fact, our Sun is destined to become a white dwarf in about 5 billion years. One of the most fascinating aspects of white dwarf is their role as cosmic chronometers. They cool at a predictable rate, allowing astronomers to estimate the ages of star clusters and even the universe itself. These stellar remnants serve as timekeepers for the cosmos. White dwarfs also responsible for one of the universe's most dramatic events, Type 1a supernova. When a white dwarf in a binary system accumulates enough mass to exceed the Chandrasekhar limit, it ignites in a powerful explosion. These supernovae are crucial for measuring cosmic distances and uncovering the secrets of dark energy. Even after a star's life ends, its planetary system may leave behind intriguing clues. Some white dwarfs retain remnants of their planets, such as debris disks or even entire planets. Studying these remnants helps us understand the fate of planetary systems, including our own. White dwarfs are natural laboratories for extreme physics. Their incredible density and gravity push the limit of quantum mechanics and relativity. By observing these stellar remnants, scientists can test fundamental theories about matter and the nature of the universe. Next, these stellar embers also hold the story of galactic evolution. Their distribution and composition reveal how stars form and evolve over the history of the Milky Way, offering a glimpse into the chemical and structural changes of our galaxy. Next, the intense gravity of white dwarfs causes light to stretch as it escapes, a phenomenon known as gravitational redshift. Observing this effect provides direct evidence of Einstein's theory of general relativity. Could life exist near a white dwarf? Some scientists theorize that planets orbiting these stellar remnants might still harbor life under certain conditions, raising intriguing questions about the longevity of life in the universe. White dwarf stars may seem like the quiet remnants of stellar life, but their significance in astronomy is immense, from helping us measure the age of the universe to unlocking the mysteries of dark energy. They remain vital to our understanding of the cosmos. Truly, these stellar embers are far more than meets the eye.
Next is for modern observation, helium-burning white dwarf. Helium-burning white dwarf is a rare and exotic type of white dwarf that burns helium in its core, unlike typical white dwarf, which are no longer undergoing nuclear fission. These white dwarfs form under unusual conditions and have distinct characteristics compared to a carbon-oxygen or oxygen-neon white dwarf. Helium-burning white dwarf emerge from the merger of two helium-core white dwarf or truth-lake helium flashes. It is generally less massive, around 0.3 to 0.5 solar masses, and larger than carbon-oxygen white dwarf, with surface temperature exceeding 100,000 K during the burning phase. Next is the Gaia satellite that launched by the European Space Agency ESA. European Space Agency ESA is a space observatory designed to create the most precise 3D map of our galaxy, the Milky Way. By measuring the position, distance, motions, and properties of over 1.8 billion stars, Gaia helps astronomers to understand more structure of the galaxy. It also allows for the detection of subtle changes in star position, revolutionizing fields like stellar dynamics, galactic archaeology, and cosmology. The Gaia satellite is an ongoing mission with periodic data releases that continue to expand our knowledge of the galaxy. Next is White Dwarf Binary System TW Pictoris. It is a cataclysmic variable star system located approximately 1,400 light years away in the constellation Pictor. Recent observation by NASA TESS, which is NASA's Transiting Exoplanet Survey Satellite, have revealed that the TW Pictoris exhibit rapid transition in brightness changes and switching between high and low luminosity modes within as little as 30 minutes. As a result from this observation, this provide insight into accretion process in white dwarf system and suggest parallel with transitional millicycle pulsars where similar rapid luminosity changes occur. Now we have come to the conclusion. White dwarf stars are more than just the remnants of stellar evolution. They are enduring markers of the universe history and dynamics. By studying these dance, cooling embers, we gain valuable insights into the life cycles of stars, the age of the cosmos, and the process that shapes galaxies. As silent witness to billions of years of cosmic change, white dwarfs remind us of the profound and ongoing transformation that define the universe.
That's all from us. Thank you.